Okay, so I'm hoping that we are now successfully live. I'm also hoping that if you can see and hear me, that you can just put a thumbs up into the chat and we will get started shortly. See just limited viewers at the moment, but if you can just put a thumbs up if you can see and hear me just in the chat, I'd really appreciate that. That'd be great. Thing a like as opposed to something in the chat, but I'm hoping that that I am being seen and heard. Great. All right. We're going to dive into today's session, which is on sequences and series. And just by way of saying hello, yeah, my name's Paul. Yesterday, unfortunately, we had a bit of a shambles with the technology. I did re-record the video later, and I have requested the person who helps me with my website to put that up as soon as possible. So it is all there, and the solutions for yesterday's session are also up on the website. Okay, so today's sequences and series, but before we dive in, just a quick reminder in case anyone's watching for the first time. The questions that we're going to go through are available for download on simi.education, and you can get them ideally before the live stream and have a look at them, and then they'll make a lot more sense when we go over them. If you're watching this video sort of after the fact, remember to watch it actively. In other words, pause, try the question yourself, and then let the video play again. Don't just put your music on and you'll drink your hot chocolate and sort of keep half an ear on it. You won't learn nearly as much that way. And then just lastly, if you are finding these sessions helpful, please tell your mates. Please like, share, subscribe, and let's get the word out there. Okay. Right, so we're gonna dive straight in, and as we've done every time, and as we will do each time, we're going to look at what formulae we get provided, and probably equally importantly, what formulae we don't get provided for this particular topic. So, in the case of sequences and series, we get a formula for the term of an arithmetic sequence, a formula for the term of a geometric sequence. We get a formula for the sum of an arithmetic sequence, and we get two formulae for the sum of a geometric sequence. The first one of those two is just for general use, and the second one only applies when r is between -1 and 1, and we are dealing with convergence, in other words, a sum to infinity. You'll notice that there's one formula on that page that's in red, and that's because it doesn't get provided. It's just a slight manipulation of the one that does get provided for the arithmetic sum. All that's happened is that 2a plus n minus 1d has been broken into a plus n minus 1d. And the a plus n minus 1d is obviously the nth term. So in a situation where we know our first term and our last term and how many terms there are, we can use that red formula. All right. Okay, looking then just at a couple of other ideas. Just a little thing about sigma notation, just if we can just talk about sigma notation. Remember that it's a Greek S and it stands for sum. So we are always adding things up when we see sigma notation. Just a reminder that the little letter at the bottom, the little number at the bottom is the first value that we put in for I, and the number at the top of the sigma notation is the last number we put in for I. The number at the top is not the number of terms. It will only be the number of terms if we start from 1. Right, so a little sort of memory aid, just take the top number minus the bottom number and add 1. That will always work and tell you how many terms we're actually dealing with. Okay, with sigma notation, and in fact with sequences generally, 3 terms is a sort of kind of magic number. So when I see sigma notation, I always encourage my students to write down 3 terms, because that allows us to ascertain what type of sequence we're dealing with. Right, the last type of sequence that we haven't spoken about at all yet is a quadratic sequence. And the only formula that you get given is the Tn equals an squared plus bn plus c formula, right? We can work out our values for a, b, and c by using the fact that a will be half the common second difference. 3a plus b will be the first term of the first differences. And obviously, if Tn is an squared plus bn plus c, and n is 1, then T1 is a plus b plus c. Right. Notice that those three formulae are in red. They do not get provided. Make sure you know them. Okay. Before we dive into solving some questions, I want to talk about convergence, right? And the whole idea of convergence. Okay, so here, what I've got over here is I've got a spreadsheet where I've got an A value and an R value, all right? And we can see, and so what I've got in the first column is just the term number, the second column is the term, and the third column is the sum of those terms, right? We can see that if, obviously, if A is 5 and R is 1, 2, the terms get bigger and bigger and bigger, and needless to say, the sum gets bigger and bigger and bigger as well. This graph over here, we're plotting on the horizontal axis just how many terms, and then the sort of number of terms that are being added, and then on the vertical axis, we're plotting the sum of those terms. So, for example, the sum of 3 terms in this case is just 18. Now, what you can see is that this grows very, very quickly, all right? And I'm going to just go and change the R value. Obviously, if I change the R value to 3, we now get even faster growth. Those 2,5 e plus 16 or whatever is 2,5 times 10 to the 16. Enormous numbers. The thing is clearly diverging, all right? We can see if I just scroll down in my spreadsheet here, you can see the numbers just getting bigger and bigger and bigger. They get massive. Okay, right. As we know, convergence happens when R is between -1 and 1. So I'm going to change my R value here to 0,9. And you'll see what happens is that this is actually starting to approach some fixed number. All right, I'm going to make it maybe like 0,8, just to see. And you'll see that it's actually it's converging. This one looks like it's converging to 25. And if I go down here and I have a look and I scroll down, notice what's happening. Because R is between 1 and -1, my terms are getting smaller and smaller and smaller. And so the amount that sorry, I don't know why those went 2 rands, the amount that I'm adding is getting smaller and smaller and smaller. And this particular one's getting close to 25. Okay. Just, I'm going to ask some questions and I just want you to think about it. If R was -1, let's go with -0,7. With convergence or divergence, I haven't hit the enter key yet. All right, absolutely, convergence. All right, you might be surprised to see it wiggling in like that. And the reason being, because R is negative, you'll notice that the terms alternate in sign. They're getting smaller in size, but they are alternating in sign. Okay, and so it actually approaches a fixed number, but from opposite sides. What I want to show you is that if I change the A value to say 9,000, convergence is not affected at all. Where the thing converges is affected, but not whether. All right. Let's try a different R value. For example, if R is 1,1, definitely will not converge. It will diverge, and we can see that. If R is -1,1, it will also diverge. What happens now, it actually oscillates wildly kind of outwards, because what's happening is that the terms are getting bigger and bigger, but alternating in sign. Okay, right. I'm hoping that that's helpful in terms of understanding. So the key takeaway there is just that the convergence is only dependent on R, not dependent on A. Okay, and convergence happens when we are lying between 1 and -1. Okay, sorry, make a hash of my screen change here. Sorry, folks, I've actually tried to improve my skills here, and I think I am getting slightly better, but albeit slowly. Okay, we're going to now dive into some questions, and probably make a lot of sense to start with question 1. Okay, the first question is just really a sort of just to kind of get us started. Give the next 3 terms in each of the following sequences. All right, now this one's actually, interestingly, that it's got a variable in it, but it is arithmetic. Okay, if we take this term and minus this term, we get negative 3a, and we get plus 5. Right, so it's actually growing by 5. We can see that it's growing by 5, but it's the number of a's is decreasing by 3. Right, so our next term would be 2a plus 23, and the next term would be negative a plus 28. All right, the a's are growing by, sorry, the a's are shrinking by 3 each time, and the constant piece is growing by 5 each time. This one is geometric. To get from, and again, if we want to check what our actual R value is, which is not what the question is asking for, it's just asking for what the next term is. If we wanted the R value, we'd take this term and divide it by this term, and we'd get negative a half y. All right, so to get from here to here, we're going to multiply by negative a half y. Right, this actually becomes negative 250 y to the 5, and our next term, 125 y to the 6. And then this last one is neither arithmetic nor geometric. To get from here to here, we've added 3, then 5, and then 7. So to get to the next term, we're going to add 9. So our next term would be 26. And to get to the next term, we're going to add 11. So our next term would be 37. So 26 and 37 are our last 2 terms. Yeah. Okay. Right, on to question 2. This says, is negative 21 a term in this sequence? Well, the first thing we've got to establish about this sequence is what type of sequence it is. If we go that, divide that, we don't get the same as that, divide that. If we go that, subtract that, we get the same as that, subtract that. This is, in fact, an arithmetic sequence. And it has a common difference of negative 3 over 2, negative 1.5. It has a first term of 19. Remember our formula for the nth term of an arithmetic sequence, a plus n minus 1 lots of d. Now what I'm going to do is I'm going to check if minus 21 fits into this sequence. It is clearly shrinking, right? It's getting smaller, so it will have some negative terms. I'm going to see what number term minus 21 is. So I'm going to make minus 21 a term, and I'm going to see where that plays out. All right, 19 plus n minus 1 lots of minus 3 over 2. Right, now we're solving an equation here, right? We started off on Thursday last week solving equations, and this has only got one variable, and it's a linear equation. It should be reasonably straightforward to solve. Okay, let's subtract 19 from both sides. We're going to get negative 40. And here we're going to get negative 3 over 2 times by n minus 1. Now, if I divide both sides by negative 3 over 2, all right, that's actually the same as multiplying by positive 2 over 3. I'm going to get 80 over 3 equals n minus 1. And obviously, if I add 1 to both sides, I'm going to get that n is 80 over 3 plus 1. Now, that is about 27,7. Right. We can't have a 27,27th term. So, in fact, the answer is no. All right. Negative 21 is not a term. It's not in the sequence. All right. And a nice sort of mathematical way of explaining why that is the case is because n needs to be a natural number. All right. And the natural numbers are 1, 2, 3, 4, 5, 6. And in this case, n is not a natural number. Okay, so it's not in the sequence. If we'd got a whole number, like 29, then it would be the 29th term, and it would be in the sequence. Okay, on to question 3. Here we've got a geometric sequence. We told 2 bits of information, and we asked to find 2 possible values of r. Okay, so we know the formula for the nth term of a geometric sequence, ar to the n minus 1. So what I'm going to do is I'm going to put both of these 2 terms into this equation. And I'm going to get 2025 equals ar to the n is 8 minus 1 is 7. Right, that's equation number 1. It's got 2 variables. I need another equation, and I'm going to get that one from here. 400 is going to equal ar to the 11. Right, now I need to solve these 2 equations. With geometric sequences, and in fact with exponential functions, when we're finding the equations of them tomorrow, not tomorrow, day after tomorrow, tomorrow's probability and counting techniques, we can actually eliminate variables by dividing the one equation by the other. Right, if we divide these 2 equations, we actually get this. We get the a's divide out, we get r to the negative 4, and over here, we're going to get 2025 over 4,000. Sorry, over 400. 2025 over 400. Okay. And now what I'm going to do is I'm going to, again, everything's linked into everything else in this subject. I want to get rid of this power of negative 4. If I could raise both sides to the negative a quarter, 2025 over 400 to the negative a quarter, right? I'm just going to bring up my calculator here, I hope. There it is. The negative a quarter. And lo and behold, I get 2/3. Now, the question asks for 2 values of r. Right? And the reason that the 2 values of r, whenever we have an even power, all right, and we undo it, we can have either the positive or the negative. Okay. If you look at the memo, I've actually divided these things the other way around, and I had something like r to the 4 equals, obviously I had r to the 4, the upside down of that. Sorry, the upside down of that. And when you find a 4th root, you can have a plus or a minus. Okay, so just be cited on that. You can check that both of those answers will actually work. Right. Question 4. An arithmetic sequence has that and that. Find the first 3 terms. Now, to find the first 3 terms, I would be able to write down the first 3 terms by new a and r. So I'm looking for 2 variables. What often applies when I'm looking for 2 variables, in fact, almost always, that's correct, simultaneous equations. So let's take a look. All right, T9 is 28. Remember, here's the formula for the nth term, a plus n minus 1 lots of d. And here's the formula for the sum of n terms. N over 2 lots of a plus n minus 1 lots of d. Okay, let's put this, the fact that T9 is 28 means that 28 is a plus 8d. Right? So I've got an equation here with 2 variables in it. I'm actually going to get a on its own from this equation. A will obviously be 28 minus 8d. Right, that's equation number 1. This is equation number 2 that I'm going to form here now by using the fact that the sum of 20 terms is 650. So 650 is 20 over 2, 2 lots of a plus 19 lots of d. This equation here also has two variables in it. Okay, I can simplify it a little bit because this becomes 10. And if I divide both sides by 10, I get 65 is 2a plus 19d. Okay, what I'm going to do next is I'm going to take this value of a, all right, and I've just about obliterated, but I'm going to pop it into there. Okay, so let's see how that's going to look. I'm now going to have an equation that looks like this. 65 is twice 28 minus 8d plus 19d. And at this stage, I might be inclined to say, aha. All right. And the cool thing, the reason I'm saying aha is I've only got one variable. All right. And this is now fairly straightforward to solve. This becomes 65 is 56 minus 16d plus 19d. I'm going to subtract 56 from both sides, and I get 9. And on the right-hand side, I get 3d. So in fact, 3d is 9. So d is in fact 3, right? I've got an equation here where I have a as the subject of the formula. So if d is 3, a is going to be 28 minus 8 lots of 3. 8 lots of 3 is 24. So in fact, a is going to be 4. You may say, I'm finished, right? A good exam strategy before you move on to the next question, just go and reread the question. Oh, no, it wanted the first 3 terms. Right, so in fact, our actual answer is going to be 4, it's the first term, 7 is the second term, and 10 is the third term. Okay, onwards and upwards to question number 5. This says, determine G if these 3 things are consecutive terms of a geometric sequence. Now, this question doesn't require any formulae. It requires us to understand that, in fact, if these are consecutive terms of a geometric sequence, then that divided by that must be the same as that divided by that. All right. So 4g plus 2 divided by g plus 3 must be the same as 5g plus 10 divided by 4g plus 2. Okay. Now, and we'll talk about this more when we do some polarity in the metric geometry. But if you've got 2 fractions that are equal, a quick way of sort of getting rid of the fractions is that the top of the one times the bottom of the other will equal the bottom of the one times the top of the other, right? So what I'm saying is that times that, 4g plus 2 all squared, is going to equal 5g plus 10 times g plus 3. Right, if you didn't know that little trick, it's a nice trick to know. But obviously, if you just multiply both sides by g plus 3 and both sides by 4g plus 2, that's what you get anyway. Right. In the first lesson, when we were talking about algebra, I talked about the importance of squaring binomials properly, and I'm hoping that you've taken that on board. You square that, you take this product and double it, so that's 8g, so it's actually going to be 16g plus 4. This here is going to be 5g squared. I'm going to get 15g from my outers and 10g from my inners, so 25g plus 30. Right? I'm now going to subtract 5 from both sides, so I get 11g squared. I'm going to subtract 25g from both sides, I get minus 9g. And I'm going to subtract 30 from both sides, and I get minus 26. Okay, now let's see if we can factorize this. 11 is a prime number, so let's it's clearly got to be 11g and g, right? And I think if I use 13 and 2, all right, I definitely don't want to put the 13 here, but if I put 13 here and 2 here, I want minus 9g, so negative 22g plus 13g. There we go. And so I get my final answers now of g is minus 13 over 11 or 2. Now, again, let's just check if I've answered this question in its, completely. It says, hang on, no, it says G must be an integer, right? An integer is a whole number, positive or negative. So in fact, I need to scrap this answer. Okay. Right. Question 6, a semi-sequence. All right, there's semi down the bottom right there. A semi-sequence is one in which the terms in odd-numbered positions form an arithmetic sequence, while the terms in even-numbered positions form a geometric sequence. So here's a specific semi-sequence, right? And I'm just going to show you the ones in the first term, the third term, the fifth term, the seventh term, and the ninth term. I've underlined those ones in red. I'm going to underline the other ones in green, the second term, the fourth term, the sixth term, and the eighth term. Now, this is a made-up question. I made it up, obviously, but it's a completely fair question. It just relies on us being able to read and understand and apply what we've learned. Okay, so it's sort of unseen, but it's fair. Right? Write down the next two terms. Well, the next term is actually going to be in the green sequence. In other words, it's going to be a geometric term. So this is going a quarter, a half, 1, 2, it's doubling. So the next term will in fact be 4, right? The next term after that will be one of these red terms. It'll be an odd numbered term. It will be the next term of our arithmetic sequence that's been going 2, 5, 8, 11, 14, absolutely 17. Okay. Next question says, find the 21st term of this above sequence. Now, this just requires just a small amount of thought because, in fact, the 21st term is going to actually be T11 of the arithmetic sequence. Because they're alternating, right? Might take a little time to think about that, but it'll be the 11th term of the arithmetic sequence, all right? And the arithmetic sequence is going 2 plus 5, all right? And you might remember that the 11th term of the arithmetic sequence is actually going to be a plus 10 lots of the common difference, and the common difference there is 3. So we get 32. So 32 will be the 11th term of the arithmetic sequence, but in fact it'll be the 21st term of the semi-sequence. The next question asks us to find the sum of 19 terms of the semi-sequence. Now, because it starts with the arithmetic sequence, one more than half of them, in other words, 10 of them will be arithmetic, and 9 will be geometric. Okay, so what we're going to do, we're just going to work those out separately and add them together. So the sum of 19 terms is going to be, and I'm going to do the arithmetic one first, n over 2, so 10 over 2, 2 lots of a, remember the arithmetic one starts with 2, plus 9, and I'm not using this n here because I'm just doing the 10 arithmetic terms, so 9 lots of the common difference of 3. Plus now I must add the 9 geometric ones. Now the geometric ones start off with a quarter as my a value. Then I have my r value to the power of n, 9 of these terms, minus 1, over my r value, minus 1. So over 2 minus 1. Right, we pop all of that into a calculator. We see that we get exactly 282,75. Okay, so a slightly unusual question, but as I said, definitely a fair question for someone who knows their work and who understands what's going on. There's no substitute for understanding. But this question involves sigma notation, and I'm sure many of you know that if you've got the silver Casio, it's actually got a sigma notation button on it. And for that reason, examiners, in a bid to achieve fairness and also to achieve that, to ensure that you actually know what you're doing, examiners try to create questions where you can't simply just plug the thing into your calculator. So this is such a question. It asks us to find P We are told the answer, but P is a kind of a variable inside here. Remember, you might remember what I said, the strategy with sigma notation, a couple of things. Firstly, think about how many terms we're dealing with. In this case, 30 minus 7 is 23, plus 1 is 24. All right, makes perfect sense, as maths always does. If we started at 1 and went up to 30, clearly 30. But because we're not starting at 1, we're missing the first 6, which is why they are 24. Okay, right, next thing, write down the first 3 terms. 3 is kind of the magic number here, because, so I start off, I put 7 in for I, and I get 7p minus 1. That's my first term. Then, and really important, sigma notation is a Greek S for plus. So plus, the next term is going to be 8p minus 1. The next term is going to be 9p minus 1. 3 is enough, all right, to work out what's actually happening here. What sort of sequence is this? Okay, we know what it is. We know that it's arithmetic. We know what A is. It's arithmetic. We know A. A is, in fact, 7p minus 1. And D is any term minus the term before it. It's actually just P. So our common difference is P. We also know that the sum of 30 terms, not of 30 terms, of 24 terms, is going to be 1308. Remember this formula? This formula tells us the sum of an arithmetic sequence, n over 2, 2a plus n minus 1 lots of d. And we know that the answer is going to be 1308 when we add 24 terms. 2 lots of A is 7p minus 1, plus 23 lots of D, and D is P. How many variables in there? Net M. Only one. Okay? Eli Lordwa. All right. Now we can solve for that variable. This comes to 12. We divide both sides by 12. We actually get 109. And here we get 14p minus 2 plus 23p. We get 37p minus 2 is 109. 9, sorry. Add 2 to both sides. We get 37p is 111. And divide both sides by 111. And we get p equals 3. Okay. Right. Onwards and upwards to the next question. And now this is an important question. Right? Not that any of the others haven't been, but we've got a plant that grows 90 centimeters in the first year. Right? So after 1 year, it's 90 centimeters tall. If you were paying attention in the financial maths one, you'll know that I like to do sort of growth by 15%. I like to use a multiplier, all right? And in fact, the multiplier, I'm just going to show you something. The multiplier will be 90 times 1,15, all right? After a year, the tree is going to be 103,5, 103,5. And then this is the total height of the tree, okay? Let's look after 2 years. So I'm going to multiply that again by 1,15. All right. And I get this number, which is 119,025. 1. Now, we might at this point be tempted to say, is this arithmetic or is it geometric? What's going on here? Let's check. It's definitely not, we can see just by eye that it's not arithmetic. Let's check if it's geometric. So I'm going to go to 103,5. And I'm going to divide by 90. All right. And I get 23 over 20. Not surprisingly, I get 1,15. All right. Now I'm going to see if I get the same number when I divide 119,025 divided by 103.5. I'm testing if this is geometric. All right. And it is, okay? But in fact, this is not, although that kind of worked for us, this is not a helpful way to get the maximum height of this tree, right? Because in fact, this is completely incorrect. Okay, I was hoping to demonstrate that it was incorrect because it's actually not the height of the tree does not increase by 15% each year, right? The growth increases by 15% each year, right? So what we actually need to look at is let's look at how much it grew. And so now this is wrong. Let's look at growth. All right. So the growth in year 1 is 90. The growth in year 2 is going to be 15% of 90, right? 0.15 times 90, right? It's going to be 13.5. So in the second year, it only grows 13.5 centimeters. In the third year, it's only going to grow 0.15 of that. In other words, 15% of that. So times 0.15. Okay, and what we get this time is we get 2.025. It's easier to see what's going on here if we leave this as 90. This is 90 times 0.15, 15% of the growth from the previous year. And this is 90 times 0.15 times another 0.15. So in other words, times 0.15 squared. Okay. Now, if we think about it, this is not the height of the tree. This is the growth of the tree. The height of the tree is going to be achieved by adding these things up. All right. And what sort of sequence is this? Well, this is definitely geometric. And moreover, not only is it geometric, R is 0.15, and 0.15 satisfies being between 1 and -1. So it doesn't matter how many terms of this we add up, it's going to approach a fixed number. Right. And I'm going to just kind of go back to my spreadsheet here. All right. And if the first term was 90, right, and the growth was, the common ratio was 0.15, right, you'll see that this tree seems to be getting very close to 105, something centimeters, right? And in fact, it is, and we're going to show why it is, right? Because we are now going to use our sum to infinity formula, which is a over 1 minus r. Okay, and a is 90. R is 0.15. So I'm going to get 90 over 0.85 or 105.88 centimeters. That's to 2 decimal places. Right, and that's the height that the tree will start to approach with time. Okay, in fact, very quickly, but it actually technically never gets to that height. Right, it's a limit. Okay, right. The next question just asks how many hexagons in figure number n. Right, this one has got 1. This one, if we count them, has got 7. This one's got 19. And this one, in fact, has got 37. Right, so it's clearly not arithmetic. It's also clearly not geometric. There's only one thing it can be, and that's quadratic. Our first differences are 6, 12, and 18. So our second differences are 6 and 6. Right, now remember, A is half our second difference. Our A is going to be 6 over 2. A is in fact going to be 3. Remember, we are trying to find the nth term formula of this form. This formula gets provided. It's the only one that gets provided for this particular sequence type. Okay, now the next thing, and you need to learn this, is that 3 lots of A plus B is equal to the first term of the first differences. It's going to equal 6. Right, but I already know what A is. Okay, A is 3. So in fact, 9 plus B must be 6. So in fact, B must be minus 3. Okay, so now I know A and I know B. Putting n equals 1 into this formula in the square block here up at the top tells us that T1 is just A plus B plus C. When we talk about T1, we talk about the first term of the original sequence. So T1 is A plus B plus C. Right? I know that A is 3. I know that B is minus 3. And I know that, I know that T1 is 1. So in fact, C must be 1. And then lastly, I can write down my final answer. The nth term is 3n squared minus 3n plus 1. I always like just to check one particular one. So I'm just going to use my formula that I've worked out here. I'm going to use my formula to work out T3. If n is 3, I'm going to get 27 minus 9. 27 minus 9 is 18, plus 1 is 19. So according to my formula, T3 is 19. Let's just scroll back up and have a look. Yeah, the third one definitely has 19 hexagons in it. Okay, the next one's kind of just for fun. I just want to show you something about looking before you leap. This one's quadratic as well, right? We're asking about shaded squares, right? Which one's got 599 shaded squares? So I think the way to go here is to work out the nth term formula for the number of shaded squares, and then make that equal to 599 and solve for n. But I want to show you that, in fact, you can pick up this sort of pattern here reasonably easily. In figure 1, we've got a square of side 2. In figure 2, we've got a square of side 3. In figure 3, we've got a square of side 4. So I'm actually going to work out the number of shaded squares by taking my figure number, okay, so figure number, n, and adding 1, all right? So for figure 1, it would be 2 squared. I'm hoping you can see that this is, in fact, the number of squares of all colors in each figure. All right, so let's just test it. Figure number 4, 5 squared, there are 25 squares. Okay, now from that, if we look, let's just look at, for example, over here. In figure number 2, we need to take away one more than the figure number of white squares. So in other words, we're going to take away n plus 1. Right, that's basically taking away the bottom row of white ones in each case. And then we must take away one more to get the number of shaded squares. So just to reinforce what I've done here, this here is what I've seen as the total number of squares in the shape. This here is taking away the sort of ones on the bottom row, and the last one is taking away this sort of single one over here. And that's just a bit of mathematical insight. If we now multiply this out, we actually get n squared. We're squaring a binomial again, see how important it is, plus 2n plus 1 minus n plus 1 minus 1. And if we sort all of that out, we actually get n squared plus n minus 1. Right, and that's the nth term formula for this particular question. I suspect 98% of the population won't do it that way. They're going to say this is 1, this is 5, this is 8, and 3 is 11, this is 5, 10, 15, 19. And they're going to pick the first differences are 4, 6, and 8. And so the second differences are 2, 2, and 2. And you can proceed, as we did with the previous question, to get our nth term formula. I've just realized that I haven't completed my memo properly because I've stopped there. That's not what the question asked for. The question said, which figure will have 599 shaded squares? So now we want to work out what value of n gives us 599. Okay, we're going to subtract 599 from both sides. Right, and now on factors of 60, right, that differ by 1. Okay, and I feel bad doing this because I'm trying to factorize 600 ahead quickly and I'm struggling. So I am actually going to pull up my other Casio calculator, which will solve this for me. Okay, but otherwise, obviously, we would use our quadratic formula if you're not fortunate enough to have one of these calculators. Okay, so mode 5, 3, and we've got 1 and 1 and minus 600. And we get 24 and 25. Right, so n equals 24. Okay, if you're not lucky enough to have one of those calculators, use your quadratic formula, or you might be better at factoring than I am. Okay, onwards and upwards to question 11. Now, this is a different kind of flavor of question, a little bit of a problem-solving question on quadratic sequences, as is the next one or another one coming up. What this tells us is that we've got a quadratic sequence. That's what we're essentially dealing with. But they haven't given us the terms of it. They've given us the terms of the first differences are generated by this nth term formula. So what we are able to do is we are able to write down the first differences. When n is 1, we get 1 minus 2, we get negative 1. When n is 2, we get 1 minus 4, we get negative 3. These are the first differences. When n is 3, we get 1 minus 6, we get negative 5. Right, these are the first differences. Now, if we know the first differences, we can certainly work out the second differences. Right, remember what we're going to do? We're going to just go that minus that, or that minus that. So negative 2, negative 2, negative 2 are in fact our second differences. Now, knowing our second differences, we can get A. Because remember, A is just half our first difference. So A is in fact going to be minus 2 half, it's going to be minus 1. Okay? We also know that 3 lots of A, I'm putting the A in there, plus B will give me my first term of my first differences. In other words, it will give me this number over here, this minus 1 over here. First term of the first differences. Right, so negative 3 plus B is minus 1. Add 2 to both sides, and I get B, add negative 3 to both sides, and I get that B equals 2. Equals 2. Okay, now, I don't have the first term of the entire thing, but it does tell me that the third term is 5. So in terms of sort of a little bit of detective work here, what I know so far is that my nth term formula is A, negative 1n squared, plus B, 2n, plus C. Okay? And I know that T3 is 5. So I can now put 3 in for the n's and 5 on the left-hand side here. And I'm going to get 5 is negative 9 plus 2 lots of 3 is 6 plus C. So I get 5 is negative 3 plus C. And I add 3 to both sides and I get C equals 8. And so my final answer for my nth term formula here is negative n squared plus 2n plus 8. Okay, so it's a variation on the question, but actually I think fairly accessible. I'm trying to show you folks as many different variations as possible. Ideally, you get into the exam and the unseen question is something that you've actually seen because you've done enough practice. Okay, right, so that type of question is quite easy if you've seen it. If you've never seen anything like it in your life before, a bit trickier. Okay, question 12. and this is a similarly sort of different one on quadratic sequences. This one actually tells us that a quadratic sequence has a constant second difference of 2. Straight away, we know that its nth term formula is one of these things, an squared plus bn plus c. All right? But we also know that the constant second difference of 2, so this a value is actually half of that. A is actually going to be 1. Right. So now we actually know that in this formula that Tn is n squared plus Bn plus C. Now I've only got two variables to find, B and C. And remember, if I've got two variables, I need two equations. So what I'm going to do is I'm going to put the the fact that the fifth term is 39. 39 is 5 squared plus 5b plus c. Okay? And if you don't mind, I'm just going to change that 5 squared to 25 straight off. All right. I think it's easy enough for us to know that that's going to be 5 squared. So now that's equation number 1. I need another equation, but I also know that the 10th term is 124. So I'm going to write down my kind of black equation here. The fact that the 10th term is 124. 124 is 10 squared plus 5b, plus 10b plus c. Two equations, each with two variables. Notice that both of them have the same number of c's, so I can solve them by elimination by subtracting one from the other. I'm actually going to take number 2 minus number 1, the bottom one minus the top one. Right, 124 minus 39, minus 39, I think is 85. 100 minus 25 is 75. 10b minus 5b is just 5b, and c minus c, nothing. Again, I can say, aha, I've only got one variable left. Now I'm going to subtract 75 from both sides. I get 10 as 5b, and lastly I'm going to divide both sides by 2. By 5 to get b equals 2. Once I've got b, I can put that value for b into either equation, all right, to get my c value. And I get my c value as 4. Okay, so the final answer for the nth term of this particular thing is Tn is 1n squared plus 2n plus 4. Okay, again, an unusual question, but not difficult if you've seen it, and not difficult if you understand what you're doing. If you've only learned how to do maths as a series of kind of rules, color by number rules without thinking, then a question like this is going to find you out. Okay, try and understand what you're doing. It makes the world of difference. Right, this question asks, when is this series going to converge? Now, as I said to you earlier, as soon as I see sigma notation, I like to write down a few terms. The first term here, I is 1. So negative 2x plus 3 to the 1. Remember, it's plus, because that's what the sigma notation means. The next term is minus 2x plus 3 squared. The next term is minus 2x plus 3 cubed. And that's enough for me to know what I'm dealing with here. I'm dealing with a geometric sequence with a common ratio. If I take this divide this, or this divide this, my common ratio is negative 2x plus 3. I'm going to get convergence providing r lies between 1 and minus 1. So let's solve that. Minus 2x plus 3 is less than 1 and bigger than minus 1, right? This works exactly like an equation. I'm going to subtract 3 from all three sides, from the left, the middle, and the right. And now I'm going to divide all three sides by negative 2. But remember, when you divide or multiply by a negative with an inequality, you need to switch the sense of the inequality sign around. So this becomes positive 2. this changes around to be one of these. This becomes x, and this becomes 1. Now, we don't really like to write that like that, because we like to write the smaller number on the left. So this is much better written as 1 less than x less than 2. In other words, x is between 1 and 2. Both things actually say the same, but it's more mathematically correct by far to write the smaller number on the left. Okay. All right. And then I think maybe the last question, maybe not. Yet indeed, it is the last question. Right. This is also just a slightly different question that I thought I would show you. Maybe, hopefully it comes up. I hope it helps you. Right. So this is an arithmetic series, and we know the answer for the sum. And then they've given us this rather weird piece of information here. They say that Tn plus 2 minus Tn is always 5. So I don't really know what are they saying here. I'm just going to come up with the value of n. All right. So in other words, if n is 6, what it's saying is that T8 minus T6 is 5. Or if n is, say, 20, T22 minus T20 is 5. Right. Now, the bit of insight that's required here is to realize that this is a gap between two terms. And if the gap between two terms is 5, then D must be 2.5. Okay, there's a little bit of kind of something unusual. But again, if you've seen something like this before, then you're much better equipped. And obviously, I'm hoping that something like that comes up. I have no sight at the exam, so I'm free to make whatever, kind of give you whatever help I can, and hope that it helps. Okay, so it asks us to find the first 3 terms. Now, this is going to be easy now, because we know that the sum of 20 terms is 595. So just to remember, sum of n terms of an arithmetic sequence, n over 2, 2 lots of a plus n minus 1 lots of d. And now I'm going to put these things in. The big sort of aha moment here came from realizing that I knew what d was. Okay, before that, I was in a world of trouble. Right, 20 over 2, 2 lots of a, right? I don't know a, and I don't have another equation, so this is not about simultaneous equations. Well, I guess maybe we could call this one a little equation, but a sort of generalized equation. So this is going to be 19 lots of 2.5. And if we work all of this out, this comes to 595 equals 10 lots of 2a plus, this comes to 47.5 when we multiply 19 by 2.5. Divide both sides by 10, we get 59.5. That equals 2a plus 47.5. Right, and so now we get subtract 47.5 from both sides, we get 12 is 2a, and then lastly divide both sides by 2, we get a equals 6. Right, the question actually asked for the first 3 terms. We know that d is 2.5, so 6 plus 2.5 is 8.5, plus 2.5 is 11. Okay, that brings us to the end of the questions. Just before we sign off, just a kind of a reminder and an appeal. Please, if this stuff's proving to be any use at all, please share it, like it, subscribe, like the video in the link, and yeah, and good luck. Tomorrow we are tackling probability and counting techniques, and the resource will be on the website soon if it's not already. I have asked for it to be uploaded, and so take a look at those questions, try them beforehand, and looking forward to hosting you again tomorrow afternoon. All right, have a great day, everyone. Cheers. God bless.